Is the slides visible? Students, is the slide visible?
Yes, ma'am.
So in the previous classes, I was discussing about the reliable data transfer. So in the reliable data transfer, we have seen different version, that is RDT 1.0. So what it says is RDT 1.0. So where it is set to be a reliable protocol where there is no loss of packets. Okay, and whatever the channel, it is said to be a reliable channel, and there is no loss of packets, no corruption of packets. Okay, and then RDT 2.0, so where there was some bit errors in that particular version. So in order to overcome that bit errors, we were using the acknowledgement. Okay, and then negative acknowledgement, so indicating that if you receive a positive acknowledgement, it indicates that the packet has reached the destination. Suppose if you receive a negative acknowledgement, it indicates that some bits has been corrupted, so there is some errors in the bits. Okay, and then we have seen the reliable data transfer, that is 2.1. So what it says is, so in order to identify the packet uniquely, so what we have to do is we have to add the sequence number, either 0 or 1. So 0 indicates old and 1 indicates the new packet. And then, so even the acknowledgement also needs the sequence number, so that we have seen in RDT 2.2. So acknowledgement with the sequence number. And then, so here whatever the protocols that we have used, it's a reliable data transfer protocol where you're going to call it as stop and wait. Means until the sender receives the acknowledgement for whatever the packet it has sent, so it has to wait. It has to wait, and it's going to receive the acknowledgement. But which acknowledgement? But for which packet the sender has received the acknowledgement? For which packet the sender has received the acknowledgement? So that's why we need a sequence number. And one more thing, till what time the sender has to wait to receive the acknowledgement? So that upgrading will be done in the RDT 3.0. So where in the RDT 3.0 we are using the timers. Okay, as soon as you start sending the packet, you're going to start the timer, and then you're going to set some time. Means, for example, I have set some time as 10 seconds. Within 10 seconds, you have to receive the acknowledgement for whatever the packet you have sent. Suppose if you doesn't receive within 10 seconds, then the timer will be stopped, indicating that so the packet may be lost in the middle. So again, what you have to do is you have to do the retransmission. So that's what we have seen in RDT 3.0. So this is RDT 3.0. RDT 3.0, where there is acknowledgement loss here. So you can see here, see this diagram. So packet 0 has been sent and acknowledgement has been received. Packet 1 has been sent, the acknowledgement is lost. And here we have started the timer as soon as you send the packet. So after some time, so there is some timeout, so indicating that the packet may not be reaching the destination. So that's why you're going to resend the packet. You have received the acknowledgement. So here there is an acknowledgement loss. And here in this case, you have sent the packet, okay, and then you have received the acknowledgement. Again, you have sent the packet, but acknowledgement is lost. Acknowledgement is you're going to get the acknowledgement, but already it is timeout. So since there is a timeout, so the packet will be sent again. So already the packet is existing at the receiver side. Already the packet is existing at the receiver side. So it sees that whatever the packet I have received, so it will be detected as a duplicate. So again, it's going to send back the acknowledgement. Okay, so you're going to receive the acknowledgement, but not in the time that you have set. So you have not received the acknowledgement within the specified time. So timeout is done already. So that's why you're going to retransmit the packet again and again. Okay. But at the receiver side, since the sequence number is specified for each and every packet, and there is a duplication of the packet for whatever you have received, so what it's going to do is just it's going to discard the packet instead of delivering to the upper layer. Here, there itself at the physical layer itself, it's going to detect. So the sequence number which is already existing. So what it's going to do is, so it is going to discard the packet. So this is called as the premature timeout or the delayed acknowledgement. Okay. So this and all we have seen in the previous classes. So today we'll discuss about the performance of RDT 3.0. So we have seen, so if there is a bit error, so with respect to the acknowledgement and negative acknowledgement, we are going to detect that and we are going to correct it. And we are going to identify the packets using the sequence number, and also for the acknowledgement, whatever you're going to receive, you're going to receive through the acknowledgement number. And then whatever the time that you are going to fix in order to send and receive, so with the help of the start timer and stop timer, so you can set the time and you can send and receive the acknowledgement. So the packets will be sent reliably. Reliable in the sense, even something goes wrong, even if the packet loss may occur or acknowledgement loss may occur, or there may be error. So by doing the retransmission, you are going to make the unreliable transfer to the reliable transfer. By using this acknowledgement, different versions of protocol, we have seen acknowledgement, negative acknowledgement, sequence number, acknowledgement sequence number, start timer, stop timer. So using these things, so what you're going to do is you're going to convert an unreliable data transmission to reliable data transmission. So that's why it is called as RDT 1.0, RDT 2.0, 2.1, 2.2, and RDT 3.0. Total 3 versions, and again in that subversions are there. So in 1.0 there is no any subversion. With respect to RDT2, there is RDT 2.0, 2.1, 2.2, and with respect to RDT3, there is only version that is RDT 3.0. Okay, so now it has made, now in the network communication, we have seen that the unreliable data transmission can also be converted to a reliable data transmission by retransmitting the packets. Okay, but what about the performance? The packet which has not reached the destination, so you are going to retransmit those packets. So indicating that, so this is said to be a reliable. Reliable in the sense, making your packet to reach the destination even something goes wrong in the network. So that is said to be the reliable data transmission. But here, reliable data transmission can be achieved, but what about the performance? What about the performance? So there is some drawback with respect to the performance with the protocol called as RDT 3.0. So RDT 3.0, it's correct, but performance will be reduced. The performance is going to sting. So by explaining one particular example or one particular problem, so we are going to see that how this performance will be reduced if you are going to use a protocol. RDT 3.0, we can also call it as the stop and wait protocol. Okay, how in the stop and wait protocol, we can see that there is a reduction in the performance. There is stinks in the performance. Your performance will be reduced. So let us think an example. So there is 1 Gbps link, means a channel or a link through which data is transmitted, where the link capacity is said to be 1 Gbps, means 1 GB per second data can be transmitted through that particular link. Okay. And then 15 millisecond propagation delay. So what is the delay that they have given? They have specified is 15 millisecond. And here they have specified, so you can transmit a packet where the packet size is said to be 8000 bit, means 1000 bytes. Means a packet size in terms of bytes, it is said to be the 1000 bytes. So if you convert 1000 bytes into bits, so it is of 8000 bits, because each byte is said to be 8 bit. So 1000 into 8, you are going to get 8000 bit. Means the packet size, it is given by 8000 bit. Means each packet is able to carry 8000 bits or 1000 bytes. Okay. So here we have a formula to calculate the time needed to transmit the packet into 1 Gbps link. Okay, so what D trans indicates, this is the time needed to transmit the packet. This is the time needed to transmit the packet into the 1 Gbps link. Means if you send a packet from source to destination, so what is the time taken? Okay, so that is the D transmission. It is nothing but the time needed to transmit the packet into 1 Gbps link. Where D transition means the transmission time, it is given by L by R. What is this L? L is nothing but the packet size. So packet size is 1000 bytes. If you convert the bytes into bits, so you're going to get 8000 bits. Okay, and this R indicates rate, means the transmission rate. Okay, how many bits can be transmitted per second or per unit of time? So it is about 1 Gbps. Already they have specified 1 GB means that is 1 into 10 to the power 9. Sorry, 10, yeah, 1 into 10 power 9 is nothing but 10 power 9 bits can be transmitted per second. Okay, so now the time needed to transmit the packet in the 1 Gbps link, it is given by 8 microseconds. 8 microseconds. Micro in the sense into 10 to the power of minus 6, or 8 into 10 power minus 6 seconds, or we can also call it as 8 microseconds. Okay, so now what we have to do, we have to identify the utilization factor. So what is the utilization factor? Means utilization is nothing but the fraction of time sender busy in sending. Okay, suppose if 1 Gbps link is allocated for the sender, 1 Gbps is allocated for the sender. So how much fraction of time the sender has used it efficiently? How much utilization has been done? Okay, that one we have to calculate. If we calculate the utilization factor, then we will come to know that the performance of this stop and wait protocol, or RDT 3.0 protocol. Okay, so here we have a formula called as U sender. So U sender, it's nothing but the utilization factor that you're going to calculate at the sender side. So how much fraction of time the sender will be busy in sending the packet. Okay, so that is given by the formula L divided by R. So L, we know that it is the packet size, R is the transmission rate, divided by RTT plus L by R. RTT is nothing but the round trip time. So the round trip time is nothing but the total time taken by the packet to send and receive. The total time that is taken by the packet to complete its transmission. Complete its transmission. So RTT is nothing but round trip time. So round trip time or round trip delay. So it is the amount of time it takes for a signal to be sent plus the amount of time it takes for an acknowledgement of that signal to be received. Okay, so the round trip time, or if you please note down, so the RTT is nothing but the round trip time. So the round trip time is nothing but, so it is the amount of time taken for a signal to be sent plus the amount of time taken for an acknowledgement of that signal to be received. Means for a complete communication to be happening for a signal, so the amount of time taken by a signal to send and receive an acknowledgement back, we are going to call it as the round trip time. So L divided by R. So L divided by R, you are going to get 8 microseconds. So if you convert 8 microseconds into milliseconds, you are going to get 0.008 milliseconds. Okay, 0.008. It's not milliseconds, it's just seconds. 0.008 seconds. Okay. So now in the same way, RTT plus L by R. So here, whatever the 8 microseconds already we have calculated, L by R is equal to 8 microseconds. So here this microseconds has been converted to millisecond. So 1 microsecond is equal to 0.001 millisecond. So in the same way, if it is 8 microsecond, if you convert into milliseconds, you are going to get 0.008 milliseconds. Okay, and then round trip time. So already the round trip time is given. If the round trip time is equal to 30 millisecond, so round trip time is given by 30 millisecond. Okay, and L by R, as usual we know, it is 0.008 millisecond. So if you are going to add 30 plus this 0.008 millisecond, we are going to get 30.008. Okay, 8 milliseconds. So now what is the utilization factor? So if you perform a division operation on this, so what is the utilization factor by the sender to send the packet, that is about 1000 bytes. So out of 1 Gbps link, only 0.00027% of the link is utilized, means the time is utilized. Okay, out of, if suppose there is 100%, okay, so out of that only 0.00027% of the thing, 0.0027% of the link has been utilized, means the time has been utilized to transmit. So or else how we can say is, only, see, the sender is busy in sending only 2.7 hundredths of 1% of the time. Okay, if there is 100% of the time is reserved for a sender, only 1% of the time will be utilized for sending a one packet. Okay, so what it indicates is, if we consider a throughput, in terms of throughput, only 267 kilobits per second will be utilized out of 1 gigabits per second. Okay, so out of this, what we can say is, after the observation, so out of 1 Gbps link, only 267 kilobits per second can be utilized with respect to the data transmission. Okay, so what it indicates, the performance is very less. Means what here this is, so 1 kilobyte packet for every 30 millisecond will be sent. So what it indicates, 33 kilobytes of packet will be sent per second. If there is 1 Gbps, so you are going to get only 33, you are going to utilize only 33 kilobytes of packet you are going to send. So what it says is, if there is 100% is available, then the sender is going to utilize only 1% of it. Or if you consider this, 2.7 hundredths of 1%, 1% of the time will be utilized and the remaining will be get wasted. So what it says is, the network protocol limits the use of physical resources. Even 1 Gbps link is available, only some part of it they are using. So this network protocol, that is RDT 3.0, so this protocol, it is using only some part of physical resources. Out of 1 Gbps link, it is going to utilize only 267 kilobits per second. Okay, where the remaining physical resources that is reserved for transmitting the packet is reduced. So how we can increase this? We can increase. Okay, so just this is a description about stop and wait operation. See here, the sender and the receiver will be there. First packet bit will be transmitted at time is equal to 0, and last bit transmitted time, it is given by T is equal to L by R. So L by R, it is nothing but the transmission time, that is the time required for the packet that has to be sent from source to destination. Okay, first packet bit arrives, last packet bit arrives. So until the acknowledgement is received, only one packet has been sent. See, this remaining only 1%. See, if 1 Gbps is reserved, so only 1% of that will be utilized. The remaining will be wasted. Okay, the acknowledgement will be arrived, so it is given by the formula T is equal to RTT plus L by R. RTT is nothing but it is the amount of time taken for a sender to send the data plus receiver to send the acknowledgement to the sender. So when it received at the receiver side, so one complete RTT, it is referred as. And L by R is nothing but the transmission time. That is the time needed by the packet in order to reach from source to destination. That is L divided by R. L indicates the packet size, R indicates the transmission rate. In the same way, next packet is going to be sent. Okay, so if we calculate this, the same value, whatever we have got before, the same is represented here. That is only 0.00027% of your time will be utilized out of 100% of time. Okay. So, if we consider pipeline protocol, so in order to overcome the drawback, in order to use your physical resources efficiently, utilize the physical resources efficiently, we have the pipeline protocols. Okay, so the pipeline protocols, what they are going to do is the sender is going to allow multiple packets to be in flight. Okay, even the packets has to be acknowledged. But what we are going to do is we are going to send the multiple packets in the flight. Okay, in order to reach the destination. Even there may be some more packets that has to be acknowledgement, but still we are going to send a multiple packets. Okay, so in the sense, so in case of RDT 3.0, it is called as stop and wait. So until you get the acknowledgement of the first packet, after sending the first packet, you're going to wait until you get the acknowledgement. But here in case of pipeline protocol, so multiple packets will be sent. Multiple packets will be sent instead of a single packet. Okay, that is said to be the pipeline protocol. Means one after the other, you're going to send the packets. Okay, the acknowledgement is secondary. First, what you're going to do is in order to use the network resources efficiently, physical resources efficiently, okay, in order to utilize that 1 Gbps link efficiently, so you're going to send the packet. You're going to send the packet. The range of sequence numbers must be increased. Okay, range of sequence number indicates instead of sending the one packet and waiting for that acknowledgement, you are going to send multiple packets together. Means by increasing the range of sequence number, instead of one, you're going to increase the sequence number to 1, 2, 3, 4, 5, like that. At a time, you can able to send 5 packets or 6 packets like that. So depending upon the capacity, or depending upon the channel link capacity, you are going to send the packet. And then buffering at the sender or the receiver will be required. So buffering in case of pipeline protocol. So try to incorporate the using of buffers at the sender and the receiver side. So this is a stop and wait protocol where you're going to send. You can look into this particular diagram. Okay, where looking, please all of you look into this laser pointer. So here you can see the stop and wait protocol in an operation where you're going to send a single packet through this link. But here, in case of this pipeline protocol in operation, so here using, if you use the pipeline protocol, you're going to see multiple packets in pipeline sending through the channel, and you're going to receive the acknowledged packets like this. So this is how the pipeline protocol is going to work. By sending a multiple packets in flight or by sending multiple packets in a pipeline. Okay, so there is two different forms of pipeline protocol that is available, that is go back N protocol as well as the selective repeat protocol. So we have seen that in case of this RDT 3.0, that is stop and wait protocol, so there is only 0.00027% of your time will be utilized. Suppose if you consider a pipeline protocol, there is an increased utilization here. So here you can look into this diagram, sender and the receiver. At time t is equal to 0, packet will be sent. At time t is equal to 0, 1, 2, 3 packets will be sent. So first packet bit arrives. Okay, last packet bit arrives and send the acknowledgement. So last bit of the second packet arrives, send the acknowledgement. Last bit of the third packet arrives and send the acknowledgement. So acknowledgement will be arrived. Okay, what you're going to do is, so within this particular round trip time, you have received all the acknowledgement. Means after the round trip time, the first and then second and then third, one after the other, you're going to receive the acknowledgement. So this is nothing but T is equal to total time taken. So in order to send and receive the packet, that is RTT plus L by R. So now 3-packet pipelining increases where the utilization factor will be also increased to 3. How? Because instead of L by R it is for only one packet we have seen in stop and wait protocol. But in case of pipelined protocol, either go back and or selective repeat, what you want to do increase the number of packets. So here I have increased the number of packets. That is 3 packets I'm sending. So that's why 3 into L divided by R. 3 into L is nothing but 3 packets. 3 into 1000 bytes or 3 into 8000 bits. Okay, divided by R. R already it has been given rate, the transmission rate. So divided by RTT, that is 30 millisecond plus L by R, whatever we have seen. So we are going to get 0.0024 divided by 30.008. So it is given by 0.00081. Means 3 times the utilization factor has been increased. So before it was 0.00027. So now 3 times, since you are setting the 3 packets, so 3 times the utilization factor is increased compared to the stop and wait protocol. So by looking into this utilization factor, we can say that if you increase the number of packets or if you increase the range in the sequence number, definitely there will be increased utilization. There will be increased utilization. Okay. So pipeline protocol overview. So that is go back and protocol as well as selective repeat protocol. 2 protocols are there. So in case of go back and protocol, sender can have up to n unacknowledged packets in the pipeline. So here we are going to use some window size. So what it indicates that, so if you are going to send the packets, so how many number of packets can be unacknowledged? So that number of packets that can be unacknowledgement, so that is given by the window size n. N indicates the unacknowledged packets in pipeline, means they are yet to receive the acknowledgement. Still, they have not received the acknowledgement. So why we need this limitation, or why we need this window size, limited window sizes? So until you receive the acknowledgement of these number of packets, you cannot transmit the next set of packets. In order to do the flow control, okay, that is one thing. So in order to do the flow control, we have set the window size as n. Okay, until all these packets is acknowledgement, you cannot send the next set of packets. Okay, so receiver only sends the cumulative acknowledgement. So together, the receiver is going to send the cumulative acknowledgement, and it doesn't acknowledge the packet if there is a gap. Suppose if there is a gap between, suppose if packet 0 is sent, packet 1 is sent, the packet 2, it has been lost. Then suppose even if you send the packet 3, 4, 5, what it's going to do, it doesn't send the acknowledgement if there is a gap, because the second packet has been lost. Since second packet has been lost, the acknowledgement has not been sent. And even if 3, 4, 5, even if it reaches the destination also, it doesn't send back the acknowledgement. It indicates, I'll explain with the diagram, then you will understand in the better manner. And then the sender has timer for the oldest acknowledged packet. Okay, so here whatever the timer that we have set, so the timer we're going to maintain the same as the oldest unacknowledged packet. When the timer expires, so we have to transmit all unacknowledged packets. We'll see how the go back end is going to work. So this is about the selective repeat. In selective repeat, we're going to discuss in detail, and then we are going to differentiate both. So now we'll see how the go back end is going to work. Okay, here you can see k-bit sequence number in packet header. Okay, so in the packet header, it consists of the sequence number. Okay, k-bit. It is a first bit or a second bit or a third bit. So like that, the sequence number of each and every packet or each and every bit of packet will be specified in the header. And window is of up to n. Means, so what it contains, usually the consecutive unacknowledged packets will be allowed. Okay, where that is n indicates the window size. So if it crosses that, then you cannot send the new packets. Okay. So here you can see this diagram. So there is 4 different intervals. There is green, yellow, blue as well as white. So there is 4 different intervals of packets that we can see. The first is said to be where initially the base is equal to. So what do you mean by this base value? So what do you mean by next sequence number value? So base indicates unacknowledged packets. Base indicates the unacknowledged packets. Okay, so what this go back N indicates? Go back N indicates is, so you have started the transmission of packets. For some packets, you have received the acknowledgement. For some packets, you have not received the acknowledgement. So, from which packet, go back to that particular value. From which packet you have not received the acknowledgement, from that packet, you have to start the retransmission. Okay, so go back and indicates go back to the window size value that you have specified. So go back to that particular value and again start retransmission of the packet. Go back N. So go to the value or go to the packet where you have not received the acknowledgement for that particular packet. From that packet, you have to start the retransmission, and N indicates the window size. So that is still how many number of packets that can be allowed where it is not having the acknowledgement. So N indicates the window size. How many number of packets that is allowed to have a unacknowledgement. Okay. So green indicates already acknowledged. That is 0 to base minus 1. So 0 to base minus 1. Just a minute. So this usually the packet starts with 0. This is said to be 0. And this is base minus 1. So 0 to base minus 1. So this is from this value, it's nothing but base. Base indicates these packets are not acknowledged. Sent but not yet acknowledged. This yellow bars indicates the packets has been sent but it is not acknowledged. The packets has been sent but it is not acknowledged. Okay. So base indicates the packets which is not acknowledged. So base, it is pointing to this particular value. From this particular packet, the packets has been sent, but these are not acknowledged. Okay, and next sequence number is nothing but, so these are the packets that has to be sent immediately. Okay, usable, not at send. So here the blue line indicate what it indicates, usable but not at send. Means you can send the packets immediately, but after receiving from the upper layer. So these are the packets that is usable. So next sequence number, what it indicates is you can send these packets immediately after receiving from the upper layer. That is nothing but the next sequence number. And these are nothing but not usable, because if the window size value is increased greater than n, what it indicates is until you receive the acknowledgement of all these packets, then these are not usable. Okay, here we can see 4 intervals. One is 0 to base minus 1. Other one is from this arrow mark, from base to next sequence minus 1, and then from next sequence number to base plus n. This is given by base plus n. This indicates base plus n. Okay. So 0 to b minus 1 is one interval. Base to next sequence number minus 1 is equal to second interval. And then next sequence number till base plus n. So this indicates the base plus n. So this indicates the third interval. And then the other intervals is there, no, after base plus n, after the window process. So these are said to be not usable because already the window size is said to be full. Only after receiving the acknowledgement of all these packets, then only this can be usable. Okay, so these are the 4 intervals. Green indicates 0 to base minus 1 indicates it is sent and it is acknowledged. And from base to next sequence number minus 1 indicates it has been sent but not yet acknowledged. And ns next sequence number till base plus n. So base plus n is going to give the total number, means okay, so that is the end value. So this indicates these packets can be sent immediately after receiving the packet from the above layer, that is from the application layer. And the next interval set is said to be, this is not usable because it has crossed the window size. So n indicates the window size. So this is the window size. So if you count here, so the window size is said to be 13. See here 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14. Sorry. The window size n value is equal to 14. So this is limited to 14. So in order to do the flow control, in order to achieve the flow control, so we are going to set the window size to n, indicating that the package has to be acknowledged. Okay. Acknowledgements. All packets up to including sequence number n, means all the packets has to be get acknowledged. Usually cumulative acknowledgement will be sent from the receiver and may receive the duplicate acknowledgements. Even from the receiver, some duplicate acknowledgements can also be sent. And the timer for the oldest in flight, the packet. So usually the timer will be set, okay, for the oldest packets, whatever you're going to use, the same timer value you're going to use, and within the timer, the acknowledgement has to be received. Okay, if suppose there is a timer, we have to retransmit the packet. Okay, and all the higher sequence number packet in the window. So, we'll see here. So this is how the finite state machine we can see for the go back N protocol. So go back N. So go back to the packet for which packet, from which packet you have not received the acknowledgement. From that packet, we have to start the retransmission. So that's how this go back N protocol is going to work. So I already told that in FSM. So this A symbol, so this upper arrow symbol, what this indicates is start the transmission. When we have to start the transmission of packets, when base is equal to 1 and next sequence number is equal to 1. If both are set to be same, base as well as next sequence number, it is set to be 1, it indicates that it is at the initial point. It is at the first point of the transmission. It is at the first packet of the transmission. So in that case, base is equal to 1 and next sequence is equal to 1. So now you can start the transmission. Now you can start the transmission. Now. So this is the first case. This is the first case. In the first case, you're going to receive the data from the above layer. So I told that. So this upper value indicates the event and the content below this horizontal line indicates the action that has to be taken place. So what event has been taken place now? You're going to receive the data or send the data from the above layer to the below layer. That is from application layer to the below layer. That is the transport layer. So here what we have to do, we have to check a condition. If next sequence number is less than base plus n. So here you can see this diagram. If next sequence number is less than the base plus n, means it should not cross the window size. It should not cross the window size. Only in that condition, you have to create a packet. Make a packet with next sequence number, means the packet sequence number, the data and the checksum. Okay, and that to be stored in the next sequence number and you have to send the packet. Okay, so UDT send, what you have to send? You have to send a packet where the sequence number is specified, which contains the sequence number, data and the checksum. This is one condition. Suppose there is one more condition. If B is equal to next sequence number. Here you can see base is equal to next sequence number. So at that time it indicates that you are starting your transmission of packets. You have to start the timer. And you have to keep on incrementing. Means keep on incrementing the sequence number, indicating that you should keep on sending the packet one after the other. One by one. Packet 1, packet 2, packet 3. So like that. Else. else you have to refuse the data. If this is not the condition or this is not the condition, then it indicates that already the window size is too high. What you have to do is you have to refuse the data. Only if both the condition is there, then only you have to send the packet, and then you have to start your timer, and then you should keep on sending the packet one after the other by incrementing the next sequence number. Suppose if there is a timeout, what you have to do? You have to retransmit the packet again. So what you have to do? You have to start the timer, and how usually timeout means you have not received any acknowledgement. So you have not if the packet is not acknowledgement, if your packet is not acknowledgement indicates, so that packet is said to be the base packet. Base packet indicates if it is not equal to 1. But if the base packet is said to be the packets which are sent but not acknowledged. Okay. There is a timeout. Since there is a timeout, you have to retransmit the packet, and from which phase you have to start the transmission, from which interval? From the base, and then base plus 1. You can see this diagram. Okay, if there is a timeout, already the packet has been sent, and there is a timeout, but since you have not received the acknowledgement of this yellow packets, so usually it will be pointing to the base. Base will be pointing to the unacknowledged packets. So base plus 1. If there is a timeout, you have to start the timer, you have to retransmit the packet. So base plus 1, base plus 2, base plus 3, base plus 4, base plus 5, base plus 6, and then base plus next sequence minus 1. So like that we have to do the retransmission. So that's what it is specified here. So which is the base or next sequence until the next sequence minus 1, you have to retransmit the packet. So this is one case. This is one case. And then, so all these, whatever I am discussing, this is at the sender side, okay, of the finite state machine. Suppose at the sender you have received the packet, and if it is not corrupted, so what you have to do? You have to, and if it is not corrupted and you have received the acknowledgement. So you are going to consider it as base is equal to get the acknowledgement number of the received packet plus 1. Because usually it starts with 0, 1, 2, 3, so like that. So that's why get acknowledgement number and then plus 1. So that will be stored as the base value. Suppose if B is equal to next sequence number, means both are pointing to the same packet, it indicates that you have to stop the timer. Means it indicates that there is no any unacknowledged packet. You can see, you can look into this diagram. If base is equal to next sequence number, means both are pointing to the same packet, it indicates that you have to stop the timer of the previous packet transmission. Okay, indicating that all the packets has been acknowledged. Okay, so now suppose if base is equal to next sequence number pointing to the same packet, indicates that you have to stop the timer of the old one. Okay, that's what it is specified here. If base is equal to next sequence number, stop the timer. Suppose if it is not equal to sequence number, then it indicates that you have to do the retransmission. So at that time you have to start the timer. Start timer indicates there is a retransmission required. There is a retransmission required. Suppose if you have received the packet and it is corrupted, don't do anything. If you have received the packet and it is corrupted, just don't do anything. Only after the timeout, suppose if you not received the acknowledgement, at that time only you have to do the retransmission. Suppose if you are receiving the packet and it is corrupted, don't do anything. Just so usually don't do nothing. So that's what it is specified here. No action has to be taken place. Okay, this is at the sender side. So there is 4 cases. One case is ready to send with 2 conditions. Only with next sequence number is less than the base plus n, and if base is equal to next sequence number, you have to start the timer. Second case is if there is a timeout, so what you have to do is you have to start the retransmission. Only for the packets where you have not received the acknowledgement. So that is indicated by base, and in order to increment that, you're going to keep on adding 1, 2, 3 like that for the base, and then the ending value will be next sequence number minus 1. And this is, if it is not corrupted, you're going to add that value as the base, consider that value as the base. If it is equal to sequence number, it indicates that all the packets, whatever you have sent, you have received the acknowledgement, you have to stop the timer. Else what you have to do is, you have to Start the timer indicating that there is a retransmission. Okay, and if it is corrupted, then what you have to do is, so just do nothing. Only if there is a timeout, there will be retransmission of packet. Next, at the receiver end. At the receiver end, so this indicates the start symbol. So expected sequence number is set to be 1. Send the packet where the packet should be the expected sequence number, and for the acknowledgement will be sent and the checksum will be for that acknowledgement as well as the checksum has to be sent by the receiver to the sender. So by default, it's going to send the packet as an acknowledgement, or else here it has received the packet, and if it is not corrupted, it's going to check two conditions. Receiver at the receiver side, receive the packet and it's not corrupted and it is having the sequence number as expected. Okay, receive the packet and it's the expected sequence number. Suppose if the expected sequence number is 1, and even if you have received the same packet as 1, so what you have to do is extract the data, receive the packet, extract the data, deliver the data to the above layer, and send the packet. What the send packet contains? Create a packet which is the next expected sequence number. Suppose if the next expected sequence number is 2, and the acknowledgement of this old one, that is whatever the packet that you have received as expected sequence number 1. So for this acknowledgement and the checks, okay, send the packet and also increment the expected sequence number to, if it is 1, increment to 2, if it is 2, increment to 3. So like that. So this is how at the receiver side is going to work. Okay. Always send acknowledgement for correctly received packet with highest in order sequence number. Usually whenever the acknowledgement you are going to send, so this will be the highest one. This is the highest one. And it may also generate a duplicate acknowledgement, but need only remember the expected sequence number. So, and while sending the acknowledgement number, what you have to do is you have to send the expected sequence number. Okay, this is how the go back end is going to work. Suppose if it's out of order packet, what you're going to do? Discard it. No receiver buffering will be done in go back end. Okay, just re-acknowledgement packet with highest in order sequence number. Means while sending a acknowledgement, first one, what you're going to do? Packet 0 you have received, the acknowledgement will be sent for packet 0. Packet 1 you have received, the acknowledgement will be sent for packet 1. Packet 2 you have not received, the packet 2 is lost, but the acknowledgement will be sent as acknowledgement 1. Packet 3 you have received, but you are going to send the acknowledgement as acknowledgement 1. Because since the second packet you have not received, you won't send the acknowledgement to the receiver. Okay, here you can see this. Sender window n is equal to 4. Here the window size means at a time I am going to send the 4 packets 0, 1, 2, 3. Okay, so there is total 8 packets here. This blue, so whichever that has been highlighted in blue color, so this is indicated as the packets that you want to send. That is 0, 1, 2, 3. So 0th packet you are going to send packet 0 at the sender side, send packet 0. At the receiver side, receive packet 0, send the acknowledgement. Okay, packet 1 has been sent, so receive the packet 1, send the acknowledgement. Packet 2 has been sent, but here there is a loss, so no acknowledgement has not been sent for packet 2. Send packet 3, wait. So here it is going to discard that packet because the expected packet is 2, but here it is sending 3. So that's why it is discarding the packet and resending the highest acknowledgement, that is said to be 1, which is the packet that has been acknowledged. That is acknowledgement 1. Acknowledgement 2 you can't send because you have not received the packet 2. So again the packet 4 has been sent, but it will be discarded because the expected packet is 2. And it's going to send the acknowledgement of the previous one, whichever you have received. In the same way, it happens for packet 5. Okay, ignore the duplicate acknowledgement. So here the duplicate acknowledgement will be sent. So 0, 1 it is fine, but instead of 2, what acknowledgement I am receiving? I am receiving the acknowledgement again and again. That is acknowledgement 1 again and again. So now there is a timeout. Okay, usually whenever you are going to send a packet, there will be timer will be started. Okay, and whatever the acknowledgement you have received, so here the window size will be shifted to the next set. So now here you have received the acknowledgement of packet 0. So now the window will be moved to the next step. So initially it was 0, 1, 2, 3. So after receiving the acknowledgement 0, so the window will be shifted to 1, 2, 3, 4. And now we have received the first acknowledgement, so it will be 0, 1, and the window will be shifted to 2, 3, 4, 5. Okay, as soon as you receive the acknowledgement, the window will be shifted. Okay, now you are sending in the next time set. So you are sending 2, 3, 4, 5. The packet 2 time is out. So from the packet 2, actually 3, 4, 5 has reached the destination, but the expected packet was packet 2. So that's why it's going to discard even the packet it has received. So there is some drawback here also in case of go back N. All the packets has been received. Except the packet 2, other packets has been received. But here the expected packet number is set to be 2, so that's why it's going to discard all other packets. But in the next time slot, 2, 3, 4, 5 will be sent. For all the 4, the acknowledgement will be received. Okay, this is how the go back N is going to work. The go back N protocol is going to work. Okay, so in the next class, we are going to discuss about the selective repeat. Okay, thank you, students.
Ma'am, English ನಾನು ಚೆಕ್ ಮಾಡಿಲ್ಲ ಇನ್ನ